Okay, so welcome everyone to our probability webinar. So before starting, I just want to tell you that we will have a break before this this seminar, and we'll start again on August 9. Okay, and you can check on the chat the link for the next speakers. So today is a pleasure to have here with us Lucas Affonso from USP, and he's going to talk about long-range Ising model and decaying fields, a counter approach. So thank you very much, Lucas, and the screen is yours.
Okay, so thank you very much for the invitation. And today, first, I would like to say that this is a joint work with Rodrigo, Endo, and Satoshi. And today, I intended to divide this talk into 3 parts. The first one, I will review some basic features about spin lattice models. After that, I will talk about some historical remarks on the problem of phase transition using contour arguments. And after that, I will give an explanation of these contours for the long-range case and also of the Parrot's argument. So the basic definitions is that we start with the ZD lattice for dimension bigger or equal to 2. We will stay with the configuration space being this one, the omega that you are seeing there. We only have 2 spins, and the system we will be studying or talking about today is the Ising type systems that have this general form, as you are seeing by the Hamiltonian. We will be concerned only with the ferromagnetic case. This means that the coupling constants J, X, Y are all positive. They are symmetric, and they have this condition that we call regularity, that for each X, the sum of all Y in ZD that is different from X should be finite. Okay, so there are 2 main examples of this class of models. The first one is the nearest neighbor Ising model. That I guess everyone here already saw this at least once. And the other model that is very important that we will be talking today is the long-range Ising model with a polynomial decaying interaction. This means that the coupling constant decays as 1 over x minus y to the power alpha, where alpha is bigger than d. And we also have a decaying field that was studied in this nice paper by Rodrigo Bissacot, Cassandro, and Presutti, where they studied the nearest neighbor case with the decaying field, as we're seeing now. For a constant, this constant H star is positive. And they studied the phase transition, and also they studied the uniqueness for the nearest neighbor case with a decaying field. So these are the finite volume Gibbs measures, the partition function. I guess everyone already saw this. So what I mean by phase transition, if you take all the possible boundary conditions and you take the weak limit of this is the finite volume measures, you get a bunch of measures, and then you take the convex rule, you take the convex combinations, and then you take the closure of the set. This is the set of Gibbs measures. And we say that there is uniqueness when the set has only 1 measure, and phase transition when there is more than 1. And for ferromagnetic Ising systems, you can show that there are at least two ways of constructing these measures. One is if you take the plus boundary condition, and the other one is if you take the minus boundary condition. So the strategy to show phase transition is that to show that these measures that you get on the limit, on the thermodynamic limit, are different. For the phase transition, I would like to give on a risk arguments about our results. So first, let us consider these, let's say, easier configurations that are given by the sigma x that you are seeing now. That are something like this. You have a sea of minus spins, and only one ball of radius r centered at z, some lattice point z, where all the spins are plus. So you only have, let's say, bubbles of plus spins inside the minus configuration. So what happens if we look for when you look to the finite volume Gibbs measure restricted to these configurations? Well, to show phase transition, you can only look to the event of the spin at the site 0 being +1, and it's not hard to see that when you see a plus spin at the site 0, so in these configurations it has to be inside some ball, and that you have at most RD possibilities for the 0 to be inside the ball. And that the energy is proportional to the boundary of the ball. That's something like r to the power d minus 1. And since we have a decaying field and a long range interaction, we should have some different terms where this FBr is responsible for the long range interaction, and the last part here is the decaying field part. So for us to show phase transition, we first need to show that these two quantities here should be positive. So we have a competition between the long range case and the decaying field, competition between the long range interaction and the decaying field, and in this case, when we have balls, it's easy to calculate. We have this asymptotic behavior for the long range contribution that depends on the decay. So if it is between d and d plus 1, is something like r to the power 2d minus alpha. If it's larger than d plus 1, it's something like rd minus 1, and if it's alpha equals to d plus 1, it should have some logarithmic correction. We also have that the decaying field is bounded by something like r to the d minus delta. And so if you compare exponents, then you should expect something like this. That is the theorem that we actually proved, that for a fixed dimension bigger than 2, we should have a phase transition, and alpha bigger than d. We should have a phase transition for the decaying parameter of the field delta bigger than the minimum between alpha minus d and 1. But I think it's better if we look to a picture, and this is our result about phase transition. If you see on the gray region, is where we have phase transition. The x-axis is alpha minus d, the y-axis is the delta axis, and we have phase transition for all the gray region, and in the dashed line, we also have a phase transition, but the constant h star should be small. Okay, so some historical remarks are due now, and first thing, we have this paper of Katz and Thompson, where they conjectured that the one-dimensional long-range model should have a phase transition, and it was in a paper by Dyson that he proved that there was a phase transition in the one-dimensional case if the decaying parameter was between 1 and 2. And he compared with a model called a hierarchical model. So, okay. So after that, it remained under decays alpha equals to 2. And it was solved finally by Fröhlich and Spencer, using a contour argument inspired by their previous work in a different problem. And okay, we have many results after that, even using the contours, such as the papers of Imbri Neumann. You have also a paper on lattice gases by Johansson. But for this kind of a model, we have a contour argument only. We have a new result with Cassandro, Ferrari, Merola, and Presutti, where they extended the contour argument. The novelty of the result is in this sense. They extended the use of contours to prove a phase transition for a larger region of the parameters, not only for alpha equals to 2. But they needed also to use an additional condition that the nearest neighbor interaction should be large. And it was Litin in his thesis and Litin Picot that extended the argument for all the regions of the parameters. But since he based his work in the previous one, he also had this condition of the nearest neighbor interaction being large. And after that, we have a result by Bissacot, Endo, by Van Etter, Kimura, and Russell, where they proved the phase transition for the nearest neighbor. Now with the nearest neighbor interaction being 1, so it doesn't need to be large, but it has also a restriction in the decaying of the interaction. And they also studied the decays when the field is decaying. So this is all for one dimension. And what happens for multidimensional models? We have this result by Ginibri, Grossman, and Huel, where they using the usual Paros contours, they proved a phase transition using a Paros argument, but for the decaying of the interaction being larger than d+1. After that, we have also an extension of Pirogov's theory by Park, where he has more general spins. For instance, he can study the long-range Potts model in his work, but he has to restrict even more the decay of the interaction should be larger than 3d+1. After that, we have a result that is on. We have a preliminary version on arXiv. So okay. So what did we do? We start by a definition of incorrect point. So if you take a configuration and you take a point on ZD, you say that this point X is plus correct or minus correct if it is the sign of the configuration in this site and in it all of its nearest neighbor are positive if it is plus correct, or negative if it is minus correct. And the boundary of the configuration will be the set that is neither plus nor minus correct. So we call them incorrect points. So you can call them incorrect points also. So I know that this is not a usual definition, but I have a drawing that you can look at to illustrate what I'm saying. Consider now this configuration here that you are seeing, and all outside this box you have plus spins. And if you need to construct the boundary of the configuration, you should extract only the points that are minus or plus corrects. And this should give you something like this. So if you extract all the correct spins, you get something like this, and this figure is the boundary of the configuration. So in this notion of incorrectness is more usual in the Pirogov-Sinai approach, in the Pirogov-Sinai theory, and we based our contours in this case. And what happens is that once you get the boundary, oh sorry, I didn't mean to do that yet. Once you get the boundary, in order to get the contours in the usual Pirogov-Sinai theory, you usually take you only take the connected components of the boundary and say, okay, now these are our contours. But in longer range systems, you have a problem because large portions of the space can have a large interaction. The interaction sees all the lattice, so it's not so easy to break the boundary into contours. And so in order to do this, we introduced a concept that we call the MRA partition. It's something like this. You first fix real numbers M, R, A, and R. And for each configuration, with a finite boundary, of course, we will define this set that should satisfy some conditions. The first one is that they should form a partition of the boundary. And also, they have a geometric condition that says that for each gamma prime, it must be contained in only one connected component of the complement of the other gammas. What does this mean? So, if you take a look at this picture and you wanted to break this set into two parts, gamma and gamma prime, what would happen is that this partition does not satisfy condition A. Why? Because if you look to the white regions, they are the connected components of the complement of gamma. And if you look to gamma prime, it is in three different connected components, in three different white regions. So this partition violates the condition of being only one connected component of the complement. So they all should be in only one white region. And in order to fix this, you should break this into each gamma prime. Each connected component of gamma prime should be broken into another element. So the next condition is condition B, that for all gamma there is a number that is at most 2 to the power r minus 1, and a family of subsets of gamma such that gamma is the union of all these subsets. And for all distinct gamma and gamma prime, the distance between gamma and gamma prime is larger than this large quantity that you are seeing now. It's but again, I know that this may be hard to grasp in the first time, but I have more drawings to show what I mean by this. So first, let us take a look in this drawing right here, where we tried to break the gray regions. So now the gray regions for now on will be incorrect points, and let us try to break the set into two sets, gamma and gamma prime, that you are seeing in the red regions. And we will think that all these regions have diameter, all the connected regions have diameter n. For instance, we will choose m equals to 1 and r equals to 2. And in this case, if you try to make a partition, let me take blue. So if you try to make, for instance, this partition for the first case, and you take 3 guys right here, remembering that these partitions should have at most 2 to the r minus 1, then this should be 3 in this case. So I can only break gamma prime into 3 sets. We have that the maximum diameter of one of these guys is n, and since everyone here is also n, we have the maximum diameter is n. The minimum between the two is n again. And for this partition to satisfy condition B2, the distance between them should be larger than n to the power a. But as you are seeing, I chose the distance very carefully for this to break down. So it's so this doesn't satisfy the condition B2. So, but we can have other kinds of violations of this property. For instance, if you look at this case right here, and you try to make okay for this case. In this case, I will consider that this quantity here has diameter n squared, and everyone here has diameter n. So now, in this case, you may try to do something like this. Okay, now I take this right here. So everything here has diameter n. And when we try to check the condition B2, we have that the maximum diameter of the first case, you only have one component, so it's n squared. And in the other case, you have 4 components with n diameter. So this is n. The minimum is n. So the distance should be bigger than n to the power a again. In this case, the distance is 2 times n to the power a, and you say, okay, then now this is a valid partition. But you should take care, because in order to satisfy condition B2, I had to break gamma prime into 4 components. And since in this case the r equals to 2, so 2r minus 1 equals 3 again. So this is not a valid partition. So it breaks a rule of condition B, and so it's not valid. In this case, to fix this, you should have something like this should be an element, this is another element, and this is another element, and then this would be an MRA partition. But of course, you can ask me. I did a lot of drawings, a lot of talking, but there is a way to construct something like this. I will show you in the next slide as soon as I get this thing working. Yeah, some technical problems. Now we can continue. Oh. Okay, so now we have, okay. So we always assume that this MRA partition is the finest one. This meaning that it should be contained in all the others. And because of course you can say, okay, my partition of the boundary is all of the boundary. So of course it's a MRA partition, but it's of no use for you. So so we assume also the finance partition, and we will show that you can construct a non-trivial one. So for instance, in our applications, we choose the constant a to be a max between b plus 1 plus epsilon over alpha minus d, or d plus 1 plus epsilon for epsilon bigger than 0. And r is this constant that you're seeing now. And what happens is that in the one-dimensional Fröhlich-Spencer paper, the case is that A equals to 3/2 there, and R equals to 1. So our contribution in this part is to put these two more parameters to change that can vary accordingly to your problem. So okay. So the first proposition is that if you fix real numbers, MRA, okay, and you have a configuration of a finite boundary, then you have a MRA partition. So the idea is based on a multi-scale argument where at each step we should extract from the boundary a small portion of the boundary that is distant according to the scale. What I mean by that? Again, we will see this in an example. In the first step, you should extract the parts that are too small. So, for instance, in this part right here, I will extract this guy right here because it is too small for us. This is the, let's say, the 0th step. After that, we cover all the remaining points. We cover it by cubes with side length 2. And then we extract the minimal cover. Now we will separate into subsets these cubes. We will separate them into sets if they are close according to the scale. So what do I mean by that? So I mean the following. Let me get, okay, so blue. So what do I mean? If you take two cubes here, the cubes, let's say C and C prime, I say that the cubes are close if their distance is less than m times d to a. This is the diameter of these cubes in the L1 norm, and we say that these cubes are close. So what you do is that you organize into subsets the cubes that are close. You count how much in each the subsets that are cubes. So if there are less than 2 to the power r minus 1 cubes, you extract them from the boundary. So in this case, r equals to 3. So if you have in these subsets at most 7 cubes, you should extract them. But what do you extract? You extract the set that it's covering. So in this case, we have 3 cubes, and now we extract only what these cubes are covering. So, okay. And now you get this picture. And then you go to the next scale. In the next scale, now you cover the remaining sets with cubes of side length 4. You take the minimal cover. And again, for now the cubes, now I will use red. For now, these cubes are close if their distance is less than m to d4 to the a. So the condition changes according to the scale. And if they are close and if you have less than 7 cubes, you should extract what they cover. So if you count this, you have exactly 7 cubes, and you will extract these guys. Okay, so we get this remaining set. We go to the next scale. Now the scale is with cubes of side length 8. And I put this case here because you don't need to extract anything if it doesn't follow the rules. You simply go to the next scale. Now with scale 16, you have 5 cubes covering the remaining set, and then you extract this case. And now you have nothing. You have the empty set, and then you stop. So what's the result? The result is that your MRA partition should be something like this: this set, this guy right here, and the other guy right here. So as you see, you can have contours inside other contours, and also you can have not contours. I use the wrong word, but in these sets you can have then one inside another, one inside another one. You can have in each one you can have more than one connected component. So okay. Let's continue. So as I was saying, since our construction is based on the Pirogov-Sinai contours, in Pirogov-Sinai you not only have the geometric information about the contours, you also need to define labels. I will say what I mean by that. And labels, they are there in order to define a compatibility between the contours. So, for instance, if you look to this picture, as I said, the gray region is the incorrect points. If you get outside the region of incorrect points, you only have correct points. And in this region of transition between the correct and incorrect points, you have only one sign, one different sign. Here I will denote red by the plus, and minus will be blue. So what happens is that, as you see, if you look to gamma 1, you have a problem of defining what is the label, and a label in the sense that what color you have in the boundary. Oh, sorry. Did someone ask a question?
No, I don't think so.
No? Okay. So let us continue. So as you see in the figure gamma 1, you have different colors. So in order to fix that, we just take the volume. So you erase every hole you have in the figure, and you only have one boundary, and this boundary will be the label. And of course, in this figure that I showed you, you have only one connected component for the volume. But in the most general case, you have many different connected components. So it's a nice fact that actually all the exterior in the sense that it's not contained in any other component, in any other connected component of gamma. All these exterior connected components have the same label. So, okay. Now we get to our definition of contours. You start with a configuration of a finite boundary, and then the contours are pairs, where one of them is a member of the MRA partition, and the other information you have is the label, and it's the label of the serial connected components. And of course, the support of the contour is the size of this element of the MRA partition. The support is the element of the MRA partition, and its size is the size of gamma. So we also need another auxiliary regions here. We need to define the volume, as you saw before. We have a plus interior, a minus interior, the interior of the contour. That is the region between colors. So I think I can go back and explain this to you. In this case, the interior of gamma 1 is the interior negative is the region between the blue regions. I will make a drawing. So you have you have this. I guess yellow is not the best color, but okay. You have this region here is the minus gamma, is the minus interior. This region right here is the plus interior. And if you take the union of them, then you have the interior of gamma 1. Okay. So let's go back. Now for the phase transition, we still need some notation. The first thing I guess everyone may guess what it is the notion of external contour. This means that its volume is not contained in any other one. And we take by E lambda plus or minus as being the set of all families of contours that are compatible. This means that the labels should match. They are all stereo, and they have the same label as plus or minus. And most importantly, they are all contained in a given set lambda, because okay. So also it's a nice fact that this construction is rigid enough to not get too many contours, because in the usual case, what happens is that when you take only connected components, you get also an exponential bounce for the number, for the entropy of the contours. But you may ask, okay, but now since these contours may not be connected, maybe you would have too many contours. But this is not the case, and we proved that the MRA partition, its construction is rigid enough to have the entropy of the contours bounded exponentially depending on the mass. Okay. So for the phase transition, first we need to define this function, this theta x sigma, that just says if the point x is plus, minus, or incorrect for a configuration. And we introduce this new measure that is just the usual finite volume Gibbs measure conditioned to the event of its boundary being minus correct. Why this? This happens because when if you had a point in the boundary to be incorrect, then for instance, if you are in minus boundary condition, and if you take a point in the boundary of lambda as being plus, then all its neighbors are also incorrect. So you have this not so good situation where you have an incorrect point outside the set lambda. So this would be problematic. So what you do is that you restrict your measure to this event, and all the contours that you get are inside lambda. And then we have this new partition function is a restricted partition function, only summing over configurations that are compatible with a given family of contours. And with compatibility, I mean that configurations where when you construct the contours, this family gamma that you fixed are a subset of it. And then we introduce the map tau. This map just erases a contour. What he's doing is that he takes I define it for families here, but you can think in the case of only one contour. You change the incorrect points on the support by minus spins, and in the plus interior you change them by a spin flip. And when you do this, what you do is that you send the plus correct points into minus correct points, the minus correct into plus correct points, but the incorrect points are still are invariant. So in this case, what happens is that you still have the same incorrect points, but different. But let's say a different match on the boundary. So it is, instead of plus, now it's minus. And now we introduce this quantity that is generalized contribution from the long range. At the beginning of the talk, I only defined this for balls, but now, of course, since the contours can be different from balls, you have the need of a different quantity. So you have this version of this is the most important definition for most important result for the phase transition, because this proposition says to you what you gain energetically when you erase a given contour. So fixing your contour, when you take the energy of the original configuration and you take the difference with the energy without this contour, you have that this energy is lower bounded by something that depends on the size of the contour, plus this long range interaction depending on the plus interior. Okay, so next slide. So now I will give a sketch of the proof. In this case, well, the first thing is the usual Pyros argument. What you do is you are looking to the event of the magnetization of the zero being +1. And of course, since you are in the minus boundary condition, you should have a contour. So this is less than the sum of all the contours. Now, when you get the decaying field, what appears is by the previous proposition, the first thing is the contour contribution, the long range contribution, and now the decaying field contribution, and you should compare both of them. And for this, we have these two nice lemmas. The first one is that generally what happens is that depending on the decay, the contribution from the long range is lower bounded by something like 2 minus alpha over d. And if you change the size of lambda for Rd, that is the size of the ball, then you recover what we saw in the beginning of the talk. We have also a lemma that, again, if you change for the ball, you get d minus delta, as in the beginning of the talk. So this is a general form for sets with different geometry. And in the first case, between d and d plus 1, what you do is when you compare these two quantities, you can get this bound. And then you can manage to prove that these quantities are positive. And after that, when you prove that this quantity is positive, it's the usual Pyros argument. You get only contribution of the contours, and then you can upper bound this by a sum depending of course the entropy and this term depending on the mass, exponential of the mass. And then if you take the inverse temperature beta large enough, in this case, depending on the constant that you are seeing now, you can manage to show that this is less than 1/2. And then with this, you finally prove phase transition. So I guess this is all for today. Thank you very much for your attention.
Okay, thank you very much. Let's take a Lucas. So we have time for questions. Are there questions to Lucas? Yeah, so Eulalia, please go ahead.
Yeah, thank you, Lucas. I got lost in one thing. So you speak about balls. So do you need that your interaction is the same in all directions, or can you treat anisotropic things, highly anisotropic, for instance, even? Because I think I didn't keep this picture. properly.
Oh, okay. Actually, this is a nice question. I guess it all breaks down to how different contours interact. So if this anisotropy of the system is something that you can control the interaction between the contours, then you can manage to prove. But I can't say to you what this condition should be like. But I guess if you want to study something highly anisotropic, you should try to control the interaction between these contours.
Okay.
Is there any other question? Yeah, so I saw that Rodrigo Bissacot raised his hand. So Rodrigo, please.
Yeah, actually, it's not really a question. It's just a remark. Lucas, please, can you go back to the definition of the map partition?
Okay.
Yes. So for those that are aware about the Fröhlich and Spencer work, okay, this is our main reference. And just to be not mysterious, this let's say these subsets in the condition B2. So you see, we use these subsets to state the condition to the distance between the sets that will be the contours after. But you see, okay, what are these let's say family of subsets? Are just the intersection of the cubes with the incorrect the regions of incorrect points. So all these pictures that Lucas showed to you, you realize that at some moment he just keep the cubes which intercept the region, right? So this family that you are seeing now in the end of the slide, the family that's given by B1 is just the intersection of the cubes with the region of incorrect points. Just this. It's not magic. It's just you see when Lucas did the scale, the multi-scale argument, you are running with the side of the cubes, but in each step you get some intersection of cubes with the regions. So these are the sets. Just this. So this construction that Lucas showed it to you is just to get these sets which we use in the condition B2. And another important thing that maybe is the main contribution of Lucas is this condition B, which says to you that you don't is not possible to get to allow too many small parts inside of the contour. This bound of the n less than or equal to r minus 1 is one of our main contributions. Otherwise, you cannot get the exponential bound for the entropy of contours. This was the last step that was very difficult to us because at some moment we more or less we are sure that we were in the right path. Let's say following from Spencer, since the year case are a particular case of this construction, but it was impossible to go further because if you don't let's say impose that, you cannot get too many small pieces inside of contours. You have to at some moment to say, okay, at maximum this quantity, and this it allow us to control the number of contours. Maybe it's a technical let's say observation for those that they are not aware, but if you read Fröhlich and Spencer, you will realize that if we erase the condition B, you cannot control the exponential growth of the number of contours. So this and in this set of B2 condition are very simple. It's just the cubes intercepting the region of incorrect points. Just this.
Okay, thank you very much, Rodrigo. Is there any other question to Lucas or comment?
Yeah. Can you?
Yeah, go ahead, Alalia.
Can you recall the relation between R and the decay of the field? There are too many things, so I get a bit. I forgot.
Here.
Here it is A. So R is for you. Okay.
Yeah, I have a very simple question, or maybe two simple questions. The first one is, because you mentioned at the beginning that you were considering the graphs as ZD. How is it important for the whole construction, or is not important at all?
Actually, this is a nice question, and let's say, well, at some steps, I think I use the isoperimetric inequality, so you should have something good enough, something like a good isoperimetric inequality, a good way to compare the boundary of set with its volume. You should have that. I don't know about the case for general graphs, but besides that, I can't say to you I can't pinpoint to you exactly where I use ZD, because I'm used to use ZD all the time, so
Yeah, because I mean, from your presentation, at least for me, was not very clear where you were using the fact that you were working with ZD. So that's why I asked this.
Yeah.
And I mean, this epsilon here, I don't remember, where does it appear again in the results, or?
Yeah, what happens is that when you fix the MRA, depending on the decay and on all the constants will depend on alpha and D for now on. And on this epsilon, if you choose it, like, okay. So for instance,
and just to understand, do you would like to have smaller the epsilon, the better for you, or is the?
No, actually, it doesn't matter. I just put there for a matter of convenience, because you can change. You can think epsilon equals to 1 if you want. But for instance, this constant C1 depends on A and R, for instance. So you have a dependence on epsilon here on the C1, and now I don't know if this gets better if you get a smaller epsilon, because it's like a messy expression for the C1. So I can say to you if it gets better if epsilon is small.
Okay. Thank you. Is there any other question or comment to Lucas? So if not, let's thank him again. So thank you very much, Lucas.
Obrigado a vocês.
Tá no archive, né?